This is video 3.2.2, and the goal of this video is to understand how to graph and use logarithmic functions. We're going to look more at natural logarithms once you get into class. So the first thing that we need to understand is the basic properties of logs. These four properties you'll want down in your notes. The first two should just be pretty simple. We're going to use them quite a bit for graphing. The second two are a little bit more complicated, the inverse properties, because they require us to understand what an inverse is and to understand these logarithms quite well. So we'll try to explain them here, but you'll also get some more explanations when you get into class. First of all, the first example, why is log base b of 1 equal to 0? Well, let's think about this. Log base 8 of 1, in the example there, is asking 8 to what power equals 1? Well, 8 to the 0 power equals 1. So this will work for no matter what the base is. If the inside of the logarithm is 1, then the power has to be 0, because the only way to get 1 is to take a number to the 0 power. The next property, log base b of b equals 1. Looking at an example here, log base 72 of 72, remember that's asking 72 to what power equals 72? Well, 72 to the first power equals 72, and that's true for whatever base you have. Whenever the base is inside of the logarithm, that will always equal 1. The next two properties, a little bit more complicated. So let's see if we can read them out and think about what they are, what they're saying. Log base b of b to the 18th. This is asking b to what power gives you b to the 18th? b to what power gives you b to the 18th? Well, the power has to be 18, of course, because b to the 18th power will give you b to the 18th power. So it's kind of like the log b and the b pretty much just cancel each other out. And we are ending up with 18 in the end. Now the same works for this next property, but it's much more tricky to understand. 15 to the power, log base 15 of 16. We're first going to analyze what that power is, that power of 15 with the logarithm in it. We're going to look at what that black box equals. That black box is asking log base 15 of 16. That is saying 15 to what power equals 16. That's what that black box is. It's the power of 15 to get an answer of 16. We'll take a look above. Above, we're being asked to take 15 to that power again. So what will we get? We'll get 16, of course, because 15 to that power, that black box, is 16. 15 to that power is 16. So the answer is 16. Again, it's simply like we pretty much canceled out the log and the base of 15, and it just left us with 16. Let's take a look at some graphs of logarithms so you can understand why these properties are going to be so helpful. So the graphs of logs. Here we have two graphs, a graph of 2 to the x, the exponential function, and graph of g to the x, log base 2 of x. So these are inverse operations, they're opposite operations, and they're inverse functions. And whenever we have inverse functions, we will always have the case where it's a reflection over the line y equals x. We simply flip everything over y equals x, and what that does is it switches all the coordinates. So notice the point 0, 1 on the 2 to the x function. That point is now down at 1, 0. It simply switched positions with x's and y's. And that works for every point on this graph. Now, what does that mean about our graphs and how are we going to graph logarithms? Well, we're going to use what we know about exponentials. First of all, we know exponential functions have horizontal asymptotes at y equals 0. Meaning I can never have 2 to the x equal to 0. What happens is logarithmic functions also have an asymptote, but now it's a vertical asymptote at x equals 0, because I can never have 0 inside of the logarithm, because I can't take a number to a power and get an answer of 0. The second thing that we're going to use, one thing to notice real quick before we move on, is that the x's and y's change spots. So again, like I talked about up in the graph above, the x's and y's will always change positions, so to speak, and order when we're talking about graphing logarithms and actually any inverse function in general. The next thing that we're going to use is that key point 0, 1 for the graph of the exponential. That works for any base. This was base 2, but it would work for any base. Any base to the power of 0 will always equal 1. And the same thing will work for the logarithms, but notice we plug 0 in for y, and we have 1 for x. So again, these coordinates switch spots, so it went from 0, 1 to 1, 0. So that key point we used to find for exponentials, we're also going to find it for logarithms, but now we're plugging 0 in for y. The next one we're going to plug in is 1. The 1 is the exponent that's quickest to find for exponential functions, because anything to the 1 power is just that base. So in this case, 2 to the first power is equal to 2. What's nice about that is if I plug it in for my logarithm, but again, I'm plugging it in for the function, not for the x, I know that log base 2 of 2 equals 1. And again, I have a quick point, and notice again the coordinates have just switched places. So these are going to be our 2 key points. And we'll kind of summarize this for any base here. So for any base, our key characteristics of a logarithmic function is it'll have a vertical asymptote at x equals 0, because you can never have 0 inside the logarithm. The 2 key points will always be when I plug in 1 for x, I will get 0 for y, because anything to the 0 power is 1. And then the next key point is when I plug in the base for x, because anything b to the first power will always equal b, so log base b of b will always equal 1. So those are going to be our 2 key points for graphing these graphs. Now this is only true, of course, when it's just log base b of x. So let's look at some more complicated ones. We'll look at one basic one, and then we'll look at some more complicated ones and how our thinking changes slightly, but not too much. So let's take a look at the graph here. We're first going to graph the vertical asymptote, and this will be at 0 because we can never have log base 3 of 0. That's not allowed. The next point will be when I plug in 1 for x, because 3 to the 0 power equals 1. And so this gives me a coordinate pair of 1, 0, a point on my graph. The next point we're going to graph is plugging in the base, because log base 3 of 3, according to that property you wrote down, is 1, because 3 to the first power is 1. A quick sketch of the graph. I'm going to graph the asymptotes and the 2 points and connect them with a nice curve. So, now what happens once we start to change things? Notice the second example. It's log base 3 of x plus 4. What we have to do is change what we plug in, because we're still going to think about what values make that inside 0 first off. When is the inside 0? When x is negative 4. That's when we have an error, and that is where my vertical asymptote will be. The next key thing we're going to look at is when is the inside 1? The inside is 1 when x is negative 3. So I'm going to plug negative 3 in because I can calculate log base 3 of 1 is always 0, because 3 to the 0 power is 1. So I've got a point, negative 3, 0. The next case I look at is when is the inside the base. The base is 3 in this case, so when is the inside the base? The inside is the base when I plug in negative 1 for x, because log base 3 of negative 1 plus 4 is log base 3 of 3, which again, 3 to the 1 power is 3. So I have a second coordinate point, negative 1, 1. Now I have my asymptote and my 2 key points. I'll sketch the graph and draw in the curve. So we're looking for when is the inside 0, when is the inside 1, and when is the inside the base. That's always what we're looking at, and we'll summarize that in class just to make sure we all have that written down. Let's take a look at another example. So we're looking for the inside. When is the inside of the logarithm 0? Well, of course, that's when x equals 0. Now we'll look for when is the inside the base. When is the inside 1? The inside is 1 when I plug in 1. So I'm going to plug in 1 and calculate. Log base 2 of 1 is 0, which is why I did that. And I get the answer of negative 1. So one point is 1, negative 1. The next point I'm going to look for is when is the inside the base. In this case, that's 2. So for this particular problem, I just simply plug in 2. And f of 2, I get negative 1 plus log base 2 of 2. I know log base 2 of 2 is 1. Calculating this out, I get 0. So my second point is 2, 0. So I have my 2 key points in my asymptote. I'll sketch in my curve, adding the 2 points and the asymptote and drawing in that arc. So one more graph we'll look at here. It's the same exact thought process. When is the inside 0? The inside is 0 when x is 1. The next thing I look at is when is the inside 1, and that's when I plug in 2. Calculating that out, I end up getting 4 minus 0, which is 4. So my one key point is 2, 4. The next case I'm going to look at is when is the inside the logarithm, the base of the logarithm, and that's in this case when I plug in 3. When I plug in 3, I get a value of 4 minus log base 2 of 2, which is 4 minus 1, because 2 to the first power is 2. I end up getting a value of 3, 3 as another key point. Graphing these 2 points and the asymptote, you'll see that it looks like the graph is going down instead of up. That is correct because of this minus. The logarithm is being subtracted, and while the logarithm gets larger and larger for bigger values of x, when we subtract 4 minus that logarithm, we're going to keep decreasing over time. This caused the graph to sort of flip. So it's a similar shaped curve, but it's flipped upside down because of the fact that it's being subtracted. So don't be afraid to see a graph that looks a little bit different and try to think about why that might be. So we're going to look at a couple more cases and just talk about domain, because that's the number one thing we have to think about is what x's are we going to plug in. So let's take a look at the domain. What we need to remember is that the inside of the logarithm can never be 0, and it actually can never be negative, because if I have a logarithm of a negative, that's saying 4 in this case to some power equals a negative answer, and that will never be true. I can never take 4 to a power and get a negative. So this restriction on the domain is that x can only be greater than -3. It can't equal -3 because then we'd have 0 in the logarithm, and it has to always be bigger than -3. So that means my vertical asymptote's at -3. The second example is the same exact thing. I cannot equal 0, and I have to always be bigger than 0. So my restriction has to be greater than 5. And of course that means my vertical asymptote is at 5, and everything will be to the right of 5 on the graph. So that's the key point no matter what logarithm you're looking at. It's always what's on the inside. We're going to look at this example when we get to class. So we're going to skip through this example real quick and go straight to your checkpoints. So your goal here is to figure out what function matches this graph that you'll be seeing sketched here. For the free response question, your goal is to find the asymptote and key points for the function. And if you can't read that very well, it says g of x equals log base 3 of x plus 4. X plus 4 is in the logarithm. So do your best to find those answers and bring your questions into class, and we'll go over these the next day.